Right, so welcome everybody. My name's Sam Hutton. I work for SR Research, who make EyeLink eye trackers, and I'm going to be talking about eye tracking data quality. Let me put my screen show on. Both what it is and also how to measure it, how to report it, and perhaps most importantly, towards the end of the talk, how you can maximize it. I'll be going through some sort of setup tips and tricks, calibration tips, things like that, that will help you make sure that you get the most from your eye trackers one way or another. So why is understanding data quality important? There are a number of reasons, and perhaps most obviously, if you understand what the key determinants of eye tracking data quality are, in other words, what makes your eye tracking data good or bad, you'll be in a much better position to be able to kind of maximize your chances of just getting the good stuff, of generating high quality eye tracking data. And if you can do that, you're in a much, much happier place for a number of reasons. Most notably, decent high quality eye tracking data equates to a much, much faster and easier analysis experience. Eye tracking researchers over the years, and partly this is because historically eye trackers were themselves just generating poor quality data, have developed a whole range of techniques for kind of cleaning and filtering and reparsing and correcting and drift correcting and all sorts of things that they can do with poor quality data that's already been collected. But these techniques are generally incredibly effortful and time consuming and often kind of error prone. And in some senses, they're also kind of cheating, because you're basically taking data that you don't like the look of and kind of mushing it and reshaping it until it fits what you do want it to look like, and then saying that's what we got. So if you can avoid these kinds of techniques for sort of dealing with poor quality data by simply collecting high quality data in the first place, you're going to have a much, much easier time. If you've got high quality data, then you will have almost by definition less data loss. And less data loss is also, for obvious reasons, a very good thing. If you lose less data, you lose less participants. It means you may need fewer participants to complete your experiment. You could have shorter experimental sessions if you're losing less data or you're spending less time trying to calibrate and things like that. And that's enormously important in all sorts of situations. For example, MRI, where there are cost implications, EEG, where things are sort of starting to dry out on the head and stuff like that. Or if you're working with infants who may just get fussy and not want to do it anymore, shorter experimental sessions is another benefit of having high quality data. And finally, good quality data just equates to better statistical power. If you've got a better ability to detect any real effects if they're there, if you've got high quality data, you've got less noise basically, all of which is a good thing. So that's perhaps the most obvious reason for being interested in data quality in the context of eye tracking. There's a related reason, which is if you understand what good quality data is and how to measure it and how to report it, you'll be able to write much more informative and useful methods and results sections, which will benefit science as a whole. It will benefit replicability. It will benefit the ability of people to read your paper and understand its implications and form their own view of its implications. So being able to understand data quality, being able to report and measure data quality is useful for general science and science reporting. And finally, if you understand what data quality is, you'll be able to critically evaluate the claims about data quality that other researchers who are publishing eye tracking data are making, and even that other manufacturers are making about their eye trackers. It's always good in science to be cynical and questioning, and it's good to be able to have the tools with which to do that. So that's really what I'm trying to kind of get across in this satellite event. I want to return to that second point briefly about being able to measure and report eye tracking data quality being a good thing for science in general. Every year at SR Research, at the beginning of the year, we do a sort of Google Scholar search, and we search for all publications that mention the word EyeLink, and we do a very long-winded and laborious process of filtering through all of those papers and extracting all of the papers that were published in a peer-reviewed journal and which genuinely actually used an EyeLink eye tracker to collect gaze data or pupil data, not publications that just happen to mention that EyeLinks are eye trackers or whatever. And this year, for various reasons, we took a sort of slightly closer look at the methods section of all of the over 1,000 publications that we identified from 2020 that used an EyeLink to collect gaze data. And we were interested in finding out more about which of our eye trackers people were using, what software people were using for stimulus presentation and stuff like that. But we also kind of noticed a few other things as we were doing this exercise, some of which are kind of relevant for this talk. So I thought I'd mention them here. The key thing that kind of leapt out when we were reading people's methods and results sections was that if people mentioned anything to do with data quality at all, for example, accuracy or precision, things like that, I'm going to come on to explain, they generally mention the sort of manufacturer claimed values. So they'd say things like, you know, an EyeLink 1000 is accurate to 0.5 of a degree and precise to 0.0001 of a degree. And if they cited anything, it would be our website or spec sheets or anything like that, or they would just simply make that claim. And while this is in many respects great advertising as far as we're concerned, because it says nice things about our eye trackers, it's generally fairly uninformative about the quality of your actual data. It's not saying anything, you know, just because EyeLinks can be accurate down to half a degree, that doesn't mean your data is accurate down to half a degree. And I think I'm getting the impression, particularly from sort of questions that we get asked at SR Research and reviewer comments that we see, that reviewers and journal editors and people like that are going to be kind of increasingly unwilling to accept that kind of claim for much longer. They want you to be able to tell them something about your data, not just the accuracy of your eye tracker, but the accuracy of the data that you collected. And again, that's really what I want to try and give you some tools to do in the course of this, this satellite event. The other thing that leapt out bizarrely from reading all of these methods section is just how happy people are to tell us endless details, or provide endless details in their methods section about the monitors they used. Why just the monitor and nothing else gets all of this special attention that's beyond me. But people will tell you the make, the model, the serial number, the size, the distance, the luminosity, endless details about monitors, but very few details about data quality. It's quite interesting. And one of the things I guess we learn from the fact that people tell us so much about their monitors is they tell us where their monitors are positioned in terms of the distance. And so many people have got their monitors too close. This is something I'm going to come back to fairly shortly. Why having your monitor at the correct distance is actually one of the critical determinants of your data quality. It's particularly spatial accuracy, less so precision. We'll come on to that in more detail in a bit. So what is eye tracking data quality? Well, Holmquist has a very nice quote. I think it's from his book. It may be from one of the papers he's written. He's written lots of nice papers on this topic. And he states, data quality is a property of the sequence of raw data, in other words, the samples, produced by the eye tracker. It results from the combined effects of eye tracker specific properties, such as sampling frequency, latency, accuracy, and precision, and participant specific properties. And this is a nice definition for a number of reasons. Firstly, it kind of introduces us to some technical terms that we're going to be looking at, things like accuracy, precision, latency, which are all relevant when assessing eye tracking data quality. And secondly, it makes it clear that there's not just one factor at play here. It's a combination of things that will combine to sum to your data quality, one of which is the eye tracker itself and its inherent qualities and abilities. But there are also participant-specific properties. For example, whether people are wearing glasses or whether they're elderly and their eyelids are drooping. Things like that could all impact on data quality. These are participant-specific properties. The one thing that I think's missing from this definition, and really, if there's, if you learn one thing from this talk, it's this: the key determinant of eye tracking data quality is not the eye tracker, it's not the participant, it's you, the researcher. Okay, you have the biggest impact on how good your data quality is, and I think that's missing from this definition, and it's a shame, because I think once you understand your role and the power you have to influence your data quality, it's empowering, and it puts you in charge, and that's a good thing because you're the researcher. So that's what data quality is. If you're thinking about eye tracking data quality or discussing it or reading papers on it, you're going to come across a whole host of complex or confusing, at least, terminology, some of which I've already been splashing around. Terms like accuracy and precision. People also talk about noise, or maybe velocity noise. It's related to precision, but sometimes is used in a different sense. People talk about resolution, which is also related to precision, but it is also sometimes used in a slightly different sense of the smallest detectable difference. But it could be spatial resolution, it could be temporal resolution. Delays and latencies are important, particularly if you're doing gaze contingent research and you want things to change depending on where the eye is, then how long it takes your eye tracker to deliver that data becomes critical. Data loss is perhaps the easiest and simplest kind of determinant of data quality that there is. Just, how much of it you've got did you manage to record? So that's a kind of an easy one. People talk about things like drift or the impact of filtering, whether that's a kind of positive impact because you're trying to filter your data to reduce noise, or a negative impact because some filtering that the eye tracker is doing is kind of somehow masking key events like microsaccades. So filtering could be positive or it could be negative depending on what people are talking about. And people even talk about the impact of parsing algorithms, like how you decide what is or isn't a saccade or a fixation, and how that can impact on eye tracking data quality. The most confusing thing is that there are no kind of rote definitions of all of these things. Different people, different researchers, and even different manufacturers can use these terms to mean slightly different things or use them in slightly different ways. And that can lead to kind of easily lead to a state of confusion. For the purposes of this talk, I'm going to concentrate on these three: accuracy, precision, and data loss, because these are probably the three most important metrics that you can calculate and that are relevant to pretty much all eye tracking data quality. And these are the things that I'm going to focus on defining and giving you tools for calculating and reporting. And these are the things that the kind of technical tips that I'll give at the end will help you to maximize. I'm going to mention in passing some of the other things, but I just don't have time to go into them in detail. So let's start with focusing on the two big ones, accuracy and precision. This is probably kind of homework for many of you, and I apologize, you've probably all seen these kind of target diagrams before. This is probably old ground, but it just helps if we're all on the same page. So here we have a kind of target, and you can think of these crosses not as where an arrow or a bullet has hit, but as a gaze sample from an eye tracker. So in other words, somebody's looking at the center of this target, and these crosses are where the eye tracker says that person is looking. And you can see that in this leftmost image, the crosses are all tightly clustered together and they are all very close to the center of the target. And we can say that in that case, the data is both accurate and precise. It's accurate because it's close to where it should be. It's precise because sample to sample, the figures are all very similar. In other words, we're not getting a large variance around here. But you could also be precise in the sense that your eye tracker is delivering very consistent data, but inaccurate. So it's consistently telling you something, but it's telling you that they're looking here, or in fact, they were trying to look here. So you're precise, but not accurate. Similarly, you could be accurate, but not precise. If you take the average of all of these x's, or the location of all of these x's, it's going to be somewhere close to the center of the target. But it's not precise because each time you ask the eye tracker where the person is looking, it gives a slightly different answer. And of course, finally, you can have the kind of nightmare scenario of low accuracy, low precision. So if you averaged all of these locations of the blue crosses, they would be nowhere near the center. And equally, every time you ask your eye tracker where is the person looking, it's giving you some kind of very different value. So those are that's a very straightforward way to kind of conceptualize the terms accuracy and precision. And in giving you that definition, I've already kind of given you strong hints as to how these things can be calculated very simply. I've talked about averaging, I've talked about variance and sort of the difference between samples and things like that. And that's what we'll come on to in a bit more detail. But I want to unpack in a bit more detail exactly what people are talking about when they're talking about the accuracy, either of an eye tracker or the accuracy of the data that the eye tracker produces. People are generally referring to spatial accuracy, which in an ideal world, you would want to define as the difference between where the eye is actually looking and where the eye tracker says the eye is looking. That would be a very useful definition of the accuracy of an eye tracker. But the problem with that definition is that we have no method by which we can know where somebody is actually looking. If we did, we wouldn't need eye trackers. We could all go home. But we can't know where somebody's looking. We can only attempt to measure where somebody's looking. And that's the second bit. That's our eye tracker. So what do we do for the first bit? Well, the kind of way people get around this is to generally define accuracy as the difference or the distance between where the eye tracker says somebody's looking and where a target is on the screen. In other words, where we hope that they're looking. So we draw a target in the center of the screen, we know its pixel coordinates, and we know what pixel coordinates the eye tracker is telling us the person is looking at. We can subtract one from the other, and that gives us our measure of accuracy. So that diagram just illustrates it. The plus is the target, it has a known pixel location. The pink circle is the gaze cursor, or where the eye tracker says the person is looking, and we can measure the distance between those two and use that as our proxy, if you like, for accuracy. Now, as I say, this definition you can see is involving assumptions, okay? It's assuming a number of things. One of the assumptions is that the person is actually looking at the target, which we'll come back to in a bit. If you're going to measure accuracy, one of the least easy sort of questions to answer, and I can't really give guidelines on this because there are no real guidelines, you can sort of use common sense, but is which bit of your data should you measure accuracy over? If you've got a target as a location, you can ask somebody to look at that target, but they may make 3 or 4 fixations while they look at that target. So are we going to average over all of those fixations, or are we going to choose one of the fixations? If we choose one fixation, which one are we going to choose? The kind of the last one? Is that the best representation of giving them all the chances they have to make corrective saccades? Or should we just choose the longest one? And if we're going to choose one fixation, then how are we defining a fixation? Because how we define a fixation is going to have a huge impact. And we know that gaze isn't stable during fixation. So here you can see there's a kind of partial blink artifact. In this fixation, which is very common, you can see a microsaccade. So if we're talking about the accuracy of a fixation, we're averaging over the location of all of the samples in that fixation, we're kind of averaging 2 different fixations here. This one and this one. There's a tiny little microsaccade in between. It's not big enough to be detected. But does it make sense to talk about the accuracy of a fixation, or should we just talk about the accuracy of samples? If we're just talking about samples, which samples should we choose? These are not straightforward questions to answer. I'm just pointing out that they are there implicitly in any attempt to kind of measure accuracy. At some point, you're going to have to choose which bits of your data you measure accuracy over. And that choice will have an impact on the values that you produce. So, as I said earlier, we're kind of assuming here that the participant is capable of accurately fixating a target. And that's a very, very strong assumption. We know the fovea is small, but it's capable of resolving 1 or 2 degrees of visual angle. And in the context of a target like this small red dot, I could kind of put my gaze there, or there, or there, or right on it. But any of those positions of gaze would allow me to perceive that target. I would feel that I am looking at that target just the same, no matter where I put it. And this is one of the reasons, as we'll see later on, why the instructions you give your participant during particularly the calibration can be really important. If you just tell your participant, look at the target, they're going to throw their eyes somewhere close to it and they will feel that they've looked at it. If you tell your participant to look at the dot in the center of the target, then you're going to try and get, be more likely to get these little corrective saccades and get them bang on target. And if you want to measure accuracy, or if you want to do a good calibration, that's critical. So that was accuracy. We can define it as the distance between a target with a known location and the location of gaze as reported by the eye tracker. What about precision, which is sometimes, I think, unhelpfully also kind of referred to or called noise? Precision is simply the reproducibility or repeatability of your data, the degree to which the repeated measurement, in other words, all of your samples, of a set of true values produces the same or similar set of measured values, regardless of the accuracy. As we've seen, you can be precise, but not accurate. Now, precision is very easy to kind of see in eye tracking data. If you plot your position data out over time, which is what eye tracking data always used to look like to people as old as me, you will see noise as this kind of random fuzziness. It looks like noise, like sort of audio noise or whatever. So here we have some nice clean EyeLink data, and here we have some noisy Tobii data. This is genuinely EyeLink data and Tobii data, but this is a very unfair comparison because they're not comparable eye trackers. That's a 300 hertz Tobii, that's a 1000 hertz EyeLink. But it illustrates the idea. This is what clean data looks like. This is what noisy data looks like. Here's data that was clean and has been artificially had noise added to it, if you like. If on the host computer you ever see the gaze cursor sort of shaking, that's noise. You can do something about that. Typically hitting the up arrow and boosting up the pupil threshold will eliminate that noise. People get into debates about which is more important for overall data quality, accuracy or precision. And the answer is they're both super important and you want them both to be as good as they can be. They both impact on data in very different ways, but both can be super important. Okay, so that's precision. Now, people, like I say, sort of also talk about noise and noise being added, noise being added by the eye tracker. And it's not particularly helpful because it kind of implies a scenario like this, where you have some kind of pure underlying signal, which has somehow had noise added to it. And it gives the impression that, somehow if we had the right maths or the right algorithms or the right cleaning sort of strategies, we could somehow extract this pure signal and eliminate the eye tracker noise. And I think one of the points I'm trying to get across is that the oculomotor system itself is, in some senses, inherently noisy. And what you want to be able to do is minimize the kind of participants' sources of noise, the eye tracker sources of noise, the researcher sources of noise. But the idea that you're going to end up with some sort of pure signal where this is a fixation and this is a saccade just isn't the case, because we all know the eye is not still during fixations. There's drifts, microsaccades, post-saccadic oscillations, all sorts of stuff is happening, and it's real. So we've talked about defining accuracy and precision, and let's look now at measuring accuracy and precision. As I say, I've kind of already hinted as to two very straightforward ways of going about this. And these are two ways that are widely used in the eye tracking literature. And that's basically to compute averages and standard deviations. So if we take this highly accurate and highly precise data, if we took the average X and Y locations of each of the samples, the blue crosses, we would end up with an average of 5, somewhere close to 5,5, which is, not surprisingly, exactly where the bullseye is, where we're hoping that the person is looking. So our measure of accuracy is simply the distance between our target at 5,5 and the average of the samples that we measured while the person was supposedly looking at the target, which came out in this case to 5.02 and 5.01. So very accurate. We could also measure the standard deviation, which, this is, first year stats, but it would be the average distance of all of these blue crosses from their average, from this. And again, that's very low. So we can say that this data is both accurate and precise, not just by looking at it, but by quantifying it. We can put numbers onto those accuracy and precision levels. What about this data? Well, again, if we measure the average of the X and the Y locations of all of the gaze samples, we will see that it's nowhere near 5,5. It's more like 6,7.5 or something. But if we measure the standard deviation, in other words, the average distance of all of these crosses from their average location, these values are still nice and low. So again, we can put numbers on this. We can say this data is precise, this precise, and inaccurate, this inaccurate. And it works for the other examples as well. This data ends up as being relatively accurate because if we average all of those locations, we get something relatively close to 5, but the standard deviations now are higher. So it's less precise, but still reasonably accurate. Whoops, and of course over here, the average X and Y, or at least the average X is nowhere near 5, the average Y isn't far off, but it's inaccurate, at least on the x-axis, and it's imprecise. And we can even say here the imprecision is worse in the y-axis, which you can kind of see, than it is on the x-axis. So a very straightforward way to compute gaze data accuracy and precision is to calculate the average of a group of samples, subtract that from the known target location, and then compute the standard deviation across those samples and report that as precision. And you can dress that up in fancy formulae, which you will see in lots of papers and books and things like that. But just to go over that again, you can define accuracy as the angle. Typically, we'll see accuracy is reported in degrees of visual angle between the location of an actual target and the measured gaze position as somebody gazed at that target. And you sum that over samples. Same for the standard deviation. If you want, you can combine the X and the Y values using Pythagoras. So this would be the equation for computing precision across both X and Y. You just square your X, square your Y, and take the square root of the lot of them. That's Pythagoras, and that gives you a single value for precision, or indeed accuracy, across X and Y. Now, I mentioned that accuracy and precision are typically reported in degrees of visual angle, but we all know that eye trackers themselves generally deliver gaze data in screen pixel coordinates. So at some point, you're going to need to understand how you get from one to the other. Now, I'm going to show you a kind of trick for getting from one to the other that you can use with EyeLink data. But in general, if you're going to kind of get into this, it's a good idea to at least understand how you would go from pixels to degrees of visual angle. And the short answer is you need to know your screen width and its height in millimeters, how many pixels it's got, and its distance in millimeters, all of which is information you should have told your host PC when you set your system up. So as long as the host PC has got that information, it will be doing its job already. That's just illustrating the idea that visual angle is often the sum of two right triangles, but you don't need to understand that. Now, before we delve into the kind of details of how you would compute accuracy in your own data, it's worth bearing in mind that if you are doing a calibration and following it with a validation, then you have a built-in accuracy check. Okay, this is exactly what the validation is doing. It is checking the accuracy of your calibration model, or the data, in other words, the data that your eye tracker is delivering at 9 or 5 or 13, however many calibration targets you're using, points with known pixel coordinates on your screen. And what it does is it returns for each of those points the accuracy. In other words, the angular distance between where the target was and where the eye tracker measured gaze to be. And what we generally advise is that you don't start recording until you've got an average error of less than ½ degree and a maximum error of less than 1 degree. And in many respects, that may be all you need to do when you're reporting your data. It's to state in your method section that data was not recorded until a 9-point calibration validation procedure had been repeated until average accuracy across the 9 positions or whatever was less than ½ degree. That might be fine. That might be all that your reviewers want. They may want more, because that, again, is only telling you how accurate your data is at that point. If the participant sneezes, falls off their chair, comes back into a different place in the head mount and the data's all off, you're not going to know about it unless you do something else. But anyway, you have a built-in accuracy check, and it's the validation. It's worth doing. Now, you've noticed that this validation is already giving you data in degrees of visual angle, which is exactly what you want. This is just accuracy, not precision. However, the values it returns are only going to be accurate if you've given the host PC the correct screen dimensions and distances, which you do in the screen configuration settings in the host software, or by making sure that your physical.ini file has the right details in it if you're using an older EyeLink 1000 or EyeLink 2. I don't have the time to go into that in detail now, but if you're unsure whether your host software knows what your screen dimensions are and you're not passing that information via your experimental script, then go to your manual and check, and you'll see all the instructions in there. Because this validation process only really tells you how accurate the eye tracker is when people did the validation, people have suggested that, you know, maybe it would be good if we all got into the habit of doing a validation at the end of the experiment as well, so we could see how much things have gone off. People tend not to do that, and instead, what people generally do or try to do is have points throughout the recording at which they can check whether this accuracy, as reported by the validation, is still relevant and valid. And that could be anything from having a fixation cross in the middle of the screen at the beginning of each trial, or using, in EyeLink world, actual drift checks, which are that kind of central dot, or it doesn't have to be central, it can be wherever you want, that occurs in between each trial recording. Basically, you don't have to have this before every trial, you can have it before every end trials. But what this does is it gives you the ability to check that the calibration model is still valid, and therefore the metrics that you had got from your validation, average error less than ½ degree, are still holding. And if they're not, if you see drift at the drift check, then you can press escape and then C to calibrate, V to validate, and you'll be back in where you were before. So these drift checks are super useful, particularly if you want to be able to, in your method section, claim not just that your data was spatially accurate at the point when you did the validation, but that it remained so throughout the recordings. Then having drift checks is what gives you that ability. Either proper drift checks in sort of EyeLink terms, or just fixation crosses where you know at that point during the trial, it's the participant's job to be trying to fixate that cross. Then you can go into your data and measure accuracy, just as I've explained before. So I'm going to really quickly just zoom through actual kind of instructions, if you like, for measuring accuracy, not via a drift check, but from data recorded. So imagine that in your task at the beginning of each trial, there's a fixation cross, and you want to measure how accurate the eye tracker is when people are looking at that fixation cross. So basically, you're going to record somebody either during your experiment or for the hell of it, looking at target or targets with known locations. And we're going to go into that data and extract the relevant bits of gaze and basically compute these accuracy and precision metrics that I've just outlined. So you can open the data in Data Viewer, and you're going to run a sample report, which is going to give you 1 row per millisecond if you were recording at 1,000 hertz, 1 row per sample. So if you're sampling at 1,000 hertz, that's 1,000 samples per second. Sampling at 500 hertz, that's 500 samples a second. The key variables, so the columns, if you like, in our report that we're going to output, we obviously need to know whose data we're looking at, what trial they're in. It's useful to know the fixation index. That's going to give us a column of 1s, 2s, 3s, and all of the 1s will be the first fixation, all of the 2s will be the second fixation. It's going to be helpful if we know that the third fixation is the one that we want to kind of measure the accuracy of. We're going to output the X and the Y location of gaze. This is, of course, in screen pixel coordinates, because that's what eye trackers deal with. But we're also going to output the resolution X and the resolution Y. These are two super useful variables, because what they are is the number of pixels per degree of visual angle at that location, or at that sample's location on the screen. Don't forget the screen is flat, so you're actually going to have more pixels per degree of visual angle the further away towards the edges of the screen you get, because, yeah, just do the maths. Screens are flat, angles aren't. So that's useful, because that's what's going to let us cheat and get from our pixels into degrees of visual angle without having to do complicated maths involving ATAN and things like that. So we're going to open that sample report in Excel or R or whatever our favorite program for processing data is. Python, mine's Excel because I'm not very clever. And we're going to see all of our data, and we're going to create 2 columns, degrees from target X, degrees from target Y. And we're just going to put in, we're going to find the samples we want. So the first fixation, or just some samples within a fixation, where we know that the person at that point is looking at a target with a known location. And we're going to subtract that known location from our data. So in the X, if we know that the person was looking, if the target was at 960, 540, we subtract 960 from the X location, and we subtract 540 from the Y location. And that's going to give us, oh, and then we divide, this is a critical thing, then divide by the resolution data, because that's what converts the pixels into degrees of visual angle. So this will give us an X and a Y value, which is the distance between where our target was, where the eye tracker said the person was looking, in degrees of visual angle. Great, that's what we want. So we do that for the first sample, and then we span that down for as many samples as there are in the fixation, or for just the 100 samples in the middle of the fixation, whichever it is. As I say, different scenarios may require you to choose different things. But what we get is 2 columns with the distance of each of the samples from the target. And then it's dead easy. We can just calculate the average, 1 for X and 1 for Y. And if we want, we can then calculate the squares of those averages and square root that, and that gives us the XY overall Euclidean accuracy measure across X and Y. And you can see that in that particular sample, on the assumption that the person was at that point trying to gaze at a target at 960, 540, on average for those samples we selected, he was half a degree away, or she was half a degree away. So that's accuracy, dead easy to measure, matter of minutes. What about precision? We've talked about precision defined as the standard deviation of the X and the Y offsets. In other words, how far away is each of the samples from the mean of all of those samples. There is another way of measuring precision, which is quite interesting, and that's called the RMS sample to sample. And that's defined as the root mean square of the distance between consecutive samples. So I'll try and illustrate that. This is a standard deviation. Here's our bunch of samples from the eye tracker. And these red lines indicate the distance of each sample from their average. In other words, the standard deviation. And you can see that in this bunch of samples on the right, those red lines are all longer. So precision as measured by standard deviation would be worse. The values would be higher. It's more imprecise because each of the samples is further from the mean of all of the samples. So that's the standard deviation, and we could calculate that very, very easily by, instead of putting average into Excel, we'll just put standard deviation into Excel, and I'll show you that in a minute. The root mean square of the angular distance sample to sample sort of is different, and here we've got exactly the same samples, but this time we've joined them up in the order in which they were collected. So you can see that there are lines of differing length here. And here again, we have the same collection of samples, but again, they've been joined up in the order in which they were collected. This is the sample to sample bit of the RMS S2S. And what you can see now is that, in fact, if we measured precision with root mean square sample to sample, this data would actually be more precise, because the average of all of these red lines is shorter than the average of all of these red lines. Some are short, some are long, but on average, these are going to come out as slightly longer. So you can see there that standard deviation measures of precision are sensitive to slightly different types of noise than the RMS sample to sample. And in fact, standard deviation is very, very sensitive to the duration of the samples over which you measure it, for kind of obvious reasons. If you measure standard deviation over 200 milliseconds, you'll get a very, very high value, whereas that's less the case for the RMS S2S measure. So I hope that makes some sense. Just to hammer that home, standard deviation is the average distance of each sample from the mean location of all of those samples, whereas RMS S2S is the average, if you like, distance between consecutive samples. Slightly different, and they're both sensitive to slightly different things. You can calculate both quite easily, and I'll show you how. Now, one of the sort of slight differences about measuring precision compared to accuracy is that you can measure precision using an artificial eye, in which case any noise that you measure, any imprecision that you measure, is clearly the fault of your eye tracker, because there's no human oculomotor system involved. I can't kind of wave my hands and say, oh, the oculomotor system is inherently noisy, because you're not measuring an oculomotor system, you're measuring an artificial eye. We provide artificial eyes with our systems that you can use for this, that have known pupil diameters and things like that. But you can buy artificial eyes. This is a robotic artificial eye that I made that you can actually use to measure accuracy because it moves. But the key point is if it has a pupil and makes a corneal reflection, then you can measure it, and you can measure precision with an artificial eye. But you can equally measure precision using data collected on real eyes. It doesn't matter which you do. Obviously, they're going to tell you different things. Again, if we're going to report precision as a standard deviation, we're going to record somebody fixating a target at a known location, going to open our data, we're going to output the same measures as before, where the eye is and the resolution X and Y. And again, for the standard deviation one, it's just as we did for the accuracy. We're going to create two columns, degrees from the target in X, degrees from the target in Y, exactly the same formula, subtract where the target was from the X, same for the Y, span it down, but instead of calculating the average of that data, we will just calculate the standard deviation. And of course, we can do Pythagoras across the X and the Y and give ourselves a single value for precision as measured by the standard deviation for both X and Y. And here you can see it's about 0.05 of a degree, which is about where I'd expect it to be for EyeLink data from a real participant. Now, you can do the same trick in Excel or R or wherever you want to calculate the root mean square sample to sample. It's just involves creating a few more columns. So now you can create columns degrees sample to sample for the X and degrees sample to sample for the Y. And the trick is you're just going to subtract one row from the row above and then divide by the average resolution, just because, to convert from pixels into degrees of visual angle. You do that for X and Y, again, span it down. You can then create 2 more columns where you square these because we want to get rid of the signs. And then you square root them, that's the root. So we've calculated the squares, we've meaned them, we've rooted the mean, and that's what you get. And again, you can combine that over x and y to give yourself a single value for root mean square, sample to sample precision, and that's down for the same data at 0.01, which again is roughly what I'd expect. So that's very quickly a very practical way of you being able to measure accuracy and precision in 2 ways in your own EyeLink data. And all it assumes is that at various points, either at the beginning or at the end or during your task, there is a point at which somebody is looking at a target that you know its location and you know that they're looking at it. The last data quality metric, I want to give you some sort of detailed tips on how to record or report, is data loss, which is very, very easy. You run a trial report in Data Viewer and you output blink count, average blink duration, and duration. Duration is just the duration of the recording. Blink count is how many times the people blinked. Don't forget, in EyeLink world, anything where the eye tracker can't see the eye is going to count as a blink, will be passed as a blink. So if you multiply the number of blinks by the average blink duration, you'll get the number of samples that you had no data for. If you divide that by the duration, you'll then get data loss expressed as a percentage. You can do that for each trial and then give yourself some overall measure of data loss across your experiment. Okay, I'm running slightly out of time, so I'm going to zoom through this. So to summarize that, accuracy and precision and data loss are key concepts in understanding data quality. We can define accuracy as the angular distance between the average X and Y locations of a bunch of samples, probably a fixation, and a target with a known X, Y location. Precision typically defined in 2 ways or measured in 2 ways, either the standard deviation of those samples or the root mean square of the angular distance between consecutive samples. And they're slightly different in what they're measuring. The big choice that there's no easy answer to is what samples do you compute these metrics over? But that's a personal choice. And data loss is very easy to compute, but don't forget that data loss includes genuine data loss, in other words, blinks. If the eye tracker can't see the eye, it can't record where the eye is. And blinks are, of course, normal and expected. You make your life easier by calibrating and validating at the start of the experiment and using drift checks at regular intervals that will allow you to ensure that the calibration model is still valid and still good. And if you do that, then you will be able to convince any reviewer and any journal editor that your data is as accurate as you say it is, all of which is good. Okay, very quickly, zoom through this. How do you maximize your data quality? There are 3 key factors, the most important of which is the participant setup, and it all boils down to this geometry, and that's what I'm going to go through. Camera setup is important. Calibration is also important. People forget that every bit of data that their eye tracker gives them is the product of a calibration model. Okay, so if your calibration model is not good, your data is not good. It may be precise, but it may not be accurate. Having poor quality calibration models will lead to poor spatial accuracy. And that's really worth bearing in mind. So get your participant setup right. The key things to measure: the relationship between the participant and the screen. The participant's eyes should not be in line with the middle of the screen. They should be in line with the top of the screen. And this is the thing I want to get across. Your screen needs to be far enough away. If it's too close, you will force people to rotate their eyes beyond the trackable range of the system, particularly when they're looking at the corners, particularly the top corners. The trackable range of the system is, in a standard desktop scenario, is only 32 degrees horizontally, about 25 degrees vertically. It's very easy, if the screen is too close, that you're going to make people rotate their eyes beyond that trackable range. I'm going to explain what the trackable range is in a minute. A good rule is that you need to measure the width of your screen and then put it at a distance that is at least 1.75 times that width. So if your screen is a 50 centimeter wide screen, it probably needs to be 90 centimeters away to fit within the trackable range of the system. And many desks aren't 90 centimeters deep, which creates a problem. So what am I talking about when I'm talking about the trackable range of the system? You can think about it as a circle that's centered on the camera lens. So typically in a desktop mounted system, the camera is going to be down here beneath the screen. And the trackable range is basically how much the eye can rotate, and that rotation still be seen and interpreted by the camera. Basically what happens if you rotate your eye too far is the corneal reflection falls off the cornea. So you can see when you've got a desktop mounted system like this, what we're trying to do is kind of fit a screen within the top of this kind of circle. And that means the screen's going to have a relatively restricted angle that you can track across. It's 32 degrees basically. Now, if you have a tower mounted eye tracker, the camera's sort of mounted up here and it looks at the eyes via a hot mirror. It's kind of like looking at the eyes from straight ahead. So the tower mount has a much bigger trackable range, 60 degrees horizontally, 40 degrees. And that's because now we're kind of fit the cameras in the center, if you like, looking straight at the eye. And we can fit our whole screen within the whole circle, not just within the top half of a circle. So we have a much bigger trackable range. Similarly, there is actually a much bigger trackable range towards the bottom of a screen than there is at the top. But because we generally want to track over the whole screen, we give the shortest trackable range, which is 32 degrees. So if your screen is too big or too close, basically the same thing, or your camera is too low or the monitor is too high, you're going to get a situation like this, where the corners, particularly the top corners of that screen, are in danger of falling outside that trackable range. And what happens? Well, this is what happens. You get corneal smearing. The lovely circular bright corneal reflection stops being a lovely bright circle and starts distorting in its shape like this, which means you get very, very random kind of locations for it, which messes up your gaze data, can create problems for precision because sample to sample, the eye tracker is trying to guess what the middle of this horrible shaped blob is. Or you can lose it completely. So here the CR is no longer being detected at all because it's fallen right off the sclera, right off the cornea onto the sclera, and you can't see it. Or the camera can't compute its center. So a good tip is to always, before you calibrate, ask your participant to look at the four corners of the screen. And as they look at those four corners, you monitor the little thumbnail images, and what you're looking to check is that you're not getting this corneal smearing. If you are, then think about where are you getting it? Are you getting it when they're looking at the top left? In which case, maybe move the monitor to the left a bit, because that way they won't have to rotate their eyes so much to look at the top left. Does that then mess up the top right? If it does, your monitor's probably too close. You should move it further away if you can, or shrink your calibrated area, which is another option. You need to get your camera to participant relationship right. Not only does it have to be the right distance, it has to be the right height. You need to make sure that when you look, put yourself in your participant's position in the chin rest or where they would normally sit, and look at the bottom of the monitor. The very first thing you should see should be the top of the camera. If you could see a gap between the bottom of the monitor and the top of the camera, then your monitor's too high or your camera's too low. You need to adjust one or the other. You'll notice that the camera is pulled forward here. And again, if your camera is pushed right up against the back of your monitor, there's probably something wrong, because your camera needs to be about 60 centimeters away. Your monitor, if it's a widescreen, needs to be about 90 centimeters away, which means there should be a gap between the back of the camera and the front of the monitor. But when you look at that from your participant's perspective, the first thing you see when you look at the top of the camera, at the bottom of the monitor, should be the top of the camera. That's very important. Obviously, your camera should be focused, and obviously you should adjust your thresholds. Adjusting thresholds is critical for reducing noise. In other words, for increasing precision. You will get noisy data if you don't have enough pixels thresholded, or if you have too many pixels thresholded. The idea is you want to capture as many of the pupil pixels as possible and as many of the corneal reflection pixels as possible, but no more. So you don't want for pupils bits like this, where there's loads of pupil that hasn't been captured, but nor do you want loads of things like this, where there's loads of shadow in the eye that has been captured. For the corneal reflection, it's generally much more robust, but avoid this kind of thing. If you can see a white halo around the corneal reflection, that's all lost data. That's all valuable information that the eye tracker doesn't know about. And basically, when the eye tracker is measuring gaze, it's computing the center of this bunch of pixels. If you've only got 5 pixels and 2 of them change sample to sample, that's going to give you a big difference in your estimate of where that thing is, which equates to noise. If you've got 500 pixels in your corneal reflection and 5,000 in your pupil, then if any of those pixels change sample to sample, it's not going to change the average. In other words, the center, which is what the eye tracker is computing. And that's what gives you this nice, stable, clean data. So if you're seeing noise, you're seeing shaky gaze cursors, whack up your pupil threshold with the up arrow, lower your corneal reflection threshold with the minus key, and you'll probably find it gets better. Avoid this by making sure you're not making people rotate their eyes beyond the trackable range. Last thing I'm going to talk about really quickly is the calibration. It's just a regression model, but it is the beginnings of all of your data. Every single gaze coordinate that is output, every bit of parsing that is done on the product, the output of this regression model. So it's really important that you get the regression model right. What is a good regression model? It's basically one that looks nice and symmetrical. So whether you're doing 5, 9, or 13 points, you should be looking at the end of your calibration for a grid of plus signs that looks something like this. If you're seeing something like this, or often you'll get something like this. This is classical corneal smearing, somebody rotating their eye too far. Then you'll be able to validate. Your data will look pretty damn good, to be honest, for the most part. But like the calibration model, by kind of having to deal with this non-linearity, it's like stretching a sheet of rubber. You can sort of stretch a non-square sheet of rubber into a square shape, but you're going to kind of create wrinkles in that rubber. And those wrinkles in the calibration surface, if you like, would equate to little inaccuracies in your gaze data across that surface. So aim for symmetricality, avoid non-symmetricality, and then you'll get a good calibration. This kind of upside down trapezoid shape is very, very common if you've got your monitor too close. It's not going to be desperately awful. You still collect perfectly good data, but you will collect perfect high quality data if you do something about that, either by moving your screen further away or adjusting its height. Last calibration tips. Generally do a manual calibration. In other words, you press the space bar for each point. Don't let the eye tracker decide when to put the next target up. You make that decision. People have empirically proven that you get better calibration models doing that way. Motivate your participant. I mentioned this right at the beginning. Ask them to look at the dot in the center of the target. That's really important. You can even cheat. Pretend that the target's going to change color and ask them to keep an eye out for that. Motivate them to make these little corrective saccades that will get their eyes bang on. Because as I said, otherwise, there's no reason why we should look at the target properly. We can see it even if we're half a degree away. So motivate your participant. You can always undo calibration points that you think aren't very good by pressing the backspace button. And the other tip is use a 5 or a 13 point if you're in remote mode. I'm going to skip past that and just conclude. There's lots of reasons why you should understand data quality. It's very, very easy to measure the key metrics, which are accuracy, precision, and data loss. You, the experimenter, are one of the biggest, if not the biggest, kind of impacts on overall data quality. How you set the participant up, how you monitor the data as it's being collected, how you motivate and instruct your participant, all of those things will have huge impact. and give yourself opportunities to recalibrate. I skipped over this point, but don't recalibrate unless you need to. People always ask me how often should we recalibrate, and the answer is you should only ever recalibrate if you need to, but you should give yourself lots of opportunities to check whether you need to, and then if you do need to, then do it. And again, you probably have your monitor too close. I'm going to leave it there. I've taken up the whole hour. I'm going to hang around for another 10-15 minutes. If people have got questions, then please do ask them. Let me turn off my recording.